morning and welcome. So we have been looking at the von Neumann Stability Analysis, and that is very important, as you have already seen, but you will see it also in exercise 5. When we want to solve the problem, then we have to respect the stability limit. If we don't do that, and I ask you to test that yourself, you will quickly see that the solution grows beyond any bound. So it's simply useless what we get out of that. So therefore we have really to watch out for that. And to understand how that is done, we have started to look at Neumann Stability Analysis. And we started off looking at the rounding error, and we saw that the rounding error has the same finite difference method as the numerical solution that we want to solve. And both of them can be developed, can be expressed as a finite sum of Fourier modes. So that was, we have been focusing on the numerical solution. So that is our numerical approximation at the grid point xj time level Tn can be expressed as the sum from L to 0 to nj minus 1. And then we have the amplitudes uk hat n. So the amplitudes are time dependent, and they are dependent. Oh, here we have then the k. Well, then we should do it with the k. Let's say the k is then the 2 pi L, if we write it in this form. So this is the k. And then we have e to the I k xj. So, and we said that is a Fourier mode. So, the one that we identified that is a Fourier mode. And what we shall do is that we plug such a Fourier mode with the amplitude u hat n. So we consider now the wave number k, e to the I k xj. So that is what we have here. That is a Fourier mode. So that is first this. And here I would like, well, first we can state that this is true for all our j's that we are considering. And since we have periodic boundary conditions, the value at 0 is the same as the value at nj. So we can consider the points 0 to nj minus 1 or 1 to nj. That is the same. Let me ask you, do you know the discrete Fourier transform? You know the Fourier transform, I know that. You have had Mathe 4, so most of you. Do you know the discrete Fourier transform? No. Okay. Of course, that's it. You can go here. We have, these are the amplitudes, and they are the Fourier coefficients. So we have, as you see, we have nj of them. From L0 to nj minus 1, that is nj of them. And we have nj grid points, and we can also go back. So we can also go back if we get to these ones. This is just a remark. Then we would have the uk hat n in that case. It would be the sum. In that case, we would sum over the j from, we could take it from 0 to nj minus 1, whatever we like. And then we would have here the ujn e to the minus I k xj. So then we would then come back. So you can go back and forth. But what we only need is this way. We need to be able to interpolate our numerical solution, and this, you can have any numbers, uj, n, for these nj grid points by trigonometric polynomials. That's all what we need. And what I showed you yesterday, right after the lecture. I want to show you that again and a little bit more. And let's see, take one after the other. So, let's see. We start with this one. Let's see. These are the cosine modes. Let's do that a little bit bigger. So here nj is 4. So just that means we have 5 breakpoints from 0 to nj equal to 4. Let's see where pointer. Anybody seeing the pointer? Here. And we have to do it this way. So we see here, so this one is the one with the wave number k2 pi, and the wavelength is 1. We said the wavelength is the wave number divided, let's see, it's 2 pi divided by the wave number, that's the wavelength, so that is 1. And then we have the green one, that has then makes 2 oscillations. So the L is 2, and the wave number is 2 pi times 2. And then we have the red one, and that is the wave number 2 pi times 3. So there you see what they look like, and this is the real part then. That is the real part of e to the ikx. Imaginary part would be the sine. So that is one thing. And the other thing that I want to show you is an example. This is an example by taking nj, is in that case is 100, random points. Just you can use that in MATLAB. And then these are random numbers, and I put them, they are normalized usually between I think 0 and 1. And I put them into a cosine so that they are spread all over. And then we can look at this. We can do essentially, you could call this is a discrete Fourier transform from this is the, it's not the frequency, it is the domain, let's see, the Fourier domain to the physical domain. So we take, and you can do that in MATLAB by the FFT, the fast Fourier transform. That is a very important algorithm to do that. It is used all over the place when you receive messages, pictures, and you see movies, you have voice. It's usually done using Fourier transform, and you'll understand quickly why. And in this example here, the real part and the imaginary part of the Fourier transform are shown. So that is the u hat is then shown, and the real part and the imaginary part of that. You see above, and they are spread all over the place. And so there we have no real pattern. And the same is true when we look at the absolute value. So we have all wave numbers, here are the wave numbers divided by 2 pi, so this is our L. And here is then the absolute value in that case of the Fourier transform. So they are spread all over the place. So that doesn't tell us too much. But if we go and change things, and we take an example where we have a certain pattern, and let's see, I have prepared one. So this here is the one that is with the round. Let's see that. So we comment that, the one that is used, and we take the one where we have, let's see, that was the wrong one. We take this one where we have a square root of cosine and times the square root of sine. And let's see, in the end, I have also checked. title. Yes, okay. Let's try that one now. So now the numbers are changed. So instead of having random numbers, we have now numbers that have a certain pattern. And now let's start with the function first. So that is this one. So this is now our function. You see clearly there is a certain periodic pattern in that. The sine squared times the cosine squared of 2 pi x. And x is between 0 and 1. You see it above. And then we can do the Fourier transform on that. And then we get the following. The real part and the imaginary part. And the real part shows has a certain significance because it has one value that is really not 0 at L equals 0. And then we have here 1, 2, 3, 4. There we have a certain contribution. And we have here at the end, it is actually at 97. We have another contribution. And the rest is essentially 0. And the imaginary part, you see, is 10 to the minus 15. That is essentially 0. So here we have only essentially 3 contributions from the real part. And then we can see what that means when we look at the absolute value. Then we see that just again for these 3 values of L, or for just for these 3 wave numbers. So they contain essentially all the information. And that is what we use when we send pictures, images, voice, and so on. We do a Fourier transform, and then we just send, in that case we need to send only 3 Fourier transforms. That's all. We don't need to send 101 values or 100 values, just 3 values. So thereby the information gets compressed. And that is the great advantage of this technique. And that is used all over, and also we use it now here, but we use it in a different sense. The way we are using it is that we just observe that we can represent our data, our numerical solution, in this way by means of Fourier modes. And then we argued yesterday these Fourier modes, so these functions here, if we consider them as a whole vector for all the x, are linearly independent. So instead of plugging in all the sum in our finite difference method, we just need to plug in one Fourier mode. And that is what we are going to do. And then we are checking whether the numerical method will amplify such a Fourier mode, then the method is unstable, or it will damp, then the method is stable. So that is then the Fourier mode that we are going to plug into our finite difference method and check that. That is what we are going to do now. So we are considering the forward time-centered space scheme, that is number 17. That can be written in the following form, so that is a little bit more convenient. And you can see the original form in 9. We had already done that, but we repeat it here because we'll need it now. So the value, now we look at the forward time-centered space scheme, just as we had derived it originally when we started with the equations. The value at bridge point xj, new time level, is equal to the approximation at the old time level plus the r, which is our stability parameter, times uj plus 1n minus 2 ujn plus uj minus 1n. And the r, that was sometimes called the von Neumann number, is the thermal diffusivity alpha times the time step divided by the grid spacing squared. So that is what we are using here. And now we start And what we're doing now, that is essentially the Fourier analysis. Before, we have been discussing around we can have this representation, and we also argued that we can have the same representation for the rounding errors, by the way. But we prefer this because then the machinery gets easier in the end. And we are starting that now. So Fourier mode is then inserted. So let's write that. So Fourier mode 31 is inserted into our finite difference method. And that is, in our case, that's just the equation that we wrote. And then we get the following, so we need a bit of space for that. So we just pick that now and do it just almost mechanically. Put this mode in here. So what we do is we replace the uj simply by this mode. So we have then so what we do is we replace the ujn by the Fourier mode. So that is what we do. And then we just start insert that. So then we have the for n plus ujn plus 1, we have the Fourier mode u at k, and that is now at the new time level. E to the I k x j. You see here, all is governed, the index here is here, and the time level here is here. Here is just n equals 1. Otherwise it's xj. And then on the right hand side, we have the value at the old time level, that is just as it is, e to the I k xj. And then we get the r. And then the first one is uj plus 1. So then we have still the uk hat n, that is not changed, but it is changed here, e to the I k xj plus 1. The next one is again easy. Of course, it's ujn. So uk hat n, e to the I k xj, and then we have uj minus n. Again, the Fourier transform is the same as the old time level, and this is now e to the I k xj minus 1. So that's it. And now we can observe a few things here. First, we can note that the xj plus 1 is xj plus delta x. And xj minus 1 is xj minus delta x. And we can also observe that the e to the I k xj plus or minus 1 is then e to the I k xj plus or minus delta x. Right? And that we can also write as e to the I k xj times e to the plus or minus I k delta x. Basic rules. And that we are going to use now. And then what we can observe is that we can factorize this here, here, and in here you have also always this term appearing. So we can factorize that. also, or you can also put it as dividing by dividing by this exponential e to the I k x j, and using what we have over there, we get now what is left then is uk hat n plus 1 on the left, and on the right we can also factorize the uk hat n, because it's appearing here, here, here. So what is left then after dividing by e to the I k x j, the first one will be a 1 plus r. And then on this term here, this is here now for the plus, it will be the e plus I k delta x will remain. And here we just get a minus 2 after dividing by e to the I k x j and factorizing u k hat n. And from here with the minus, we see that the e to the minus I k delta x survives. Okay, and then we should not forget the u k hat n. And now we have already simplified this quite a lot, but we can continue. Now we need a little knowledge about complex numbers, so that you know, we just use, in that case, Euler's formula. And that is, we have e plus and minus I k delta x to express these two. What is that? That is the cosine of k delta x plus or minus, depending on the sign, I times sine k delta x. So that is, we know from complex numbers. Then we use that. If we look for these expressions here, we see we get, when we add them, we get 2 times cosine. Here we have plus and minus signs, so the imaginary part cancels. So that means we get simply 2 cosine from these here. So from that we get we obtain then it will be then 33. The u hat k n plus 1, that is our Fourier transform at the new time level for the wave number k, is equal to 1 plus, and now we have then the cosine in there, and we have it 2 times, we argued that, so we have 2 times cosine k delta x minus 2 times u hat kn. So then we can see we can also factorize the 2, and we shall also use a little bit more, so we can also write that in the following form. We use now a trigonometric identity, so we're now using that the cosine of k delta x minus 1 that can be expressed as minus 2 the sine squared of k delta x half. So that is a trigonometric identity. So here this should be negative, the cosine is only between 1 and minus 1, and it turns out it is actually minus sine squared k delta x half. So then we get, from that, we can express then this relation also in the following form. So, 34, that the u hat kn plus 1, and we can now do following, we can divide. We can divide uk hat n, that is then equal to, what is remaining is 1. Here we have already the 2 factorized, and then what we have here, so we get altogether a minus 4 sine squared of k delta x half. And this term that we have here, that is called the amplification factor. So this term here is called amplification factor. So we have, when we give it a name, g of k delta x equal to the ratio of the Fourier transforms from the new divided by the old one, that is called amplification factor. It's similar to what we discussed for ODEs. There we have also an amplification factor. Why is it called amplification factor? Because each time we make a time step, you can see that, for example, we can see it when we do this form. So the ukn is again equal to this factor times the uk hat n minus 1. So we can apply this formula recursively, and then we see each time, for each time step, we do a multiplication by this factor. So let us write that. So now, using, let's see if we know how to do that for the other one. I think it's easier with the 33. Recursively. We get, let's see, just keep it out. U k hat. Now we start from n instead of from n plus 1. Then we do it n times. Then we get this amplification factor to the power n times the Fourier transform at the time level 0. And it's important that this here is now not a superscript, an index, but this is an exponent. So that means, that gives the name, it's each time step the solution, the previous solution is amplified, you see that in 33, by this factor. When we start from the initial value, that is the Fourier transform of the initial condition, uk hat 0, that is multiplied then n by g to the power n, to get the value at the new time level. So, then we can see what we need now. Remember, what we need is boundedness. We need boundedness of the solution. And if we want to have this bounded, then we do a similar argument as we did for ODEs. We say that the absolute value of the amplification factor must be smaller equal to 1. If it's larger than 1, this will go beyond all bounds. But if it's bounded by 1, then it's okay. So, from that, thus, if the absolute value of the amplification factor is smaller equal than 1, then we will have, look at that, if we have the absolute value of u hat kn that will be then equal to this. And if this in absolute value is small equal to 1, also the power to n equal to 1, and then we get that this is bounded by the Fourier transform of the initial condition. And we can do that for all Fourier modes, k, all Fourier wave numbers k, and then the whole solution is bounded. And we can show that actually. For those interested, it's Parseval's theorem that is used to do that. So then we have boundedness. So then we have the condition that we need to get a stable solution. So let's write that. So if we have this condition satisfied that the amplification factor in absolute value is smaller or equal than 1, we have this situation, then the numerical solution is bold un. I write it, the numerical solution at any time level n is bounded, that is the explanation of this, is bounded by its initial condition. And that was what we wanted to have for stability. Then we can estimate the solution at any time level n in terms of the initial condition. And we have now the arguments for the numerical solution, but we can have the same arguments for the rounding error, because the form of the finite difference method and the representation as some finite sum of Fourier modes is just the same. So we just note that the same, what we are saying here about numerical solution is true for the rounding error. By all that, we can conclude that the finite difference method is in that case stable. If you have this situation, then the finite difference method is stable. And all this reasoning gives us then the stability condition, what we need to require. And that is true not only for the time-centered space, but for any finite difference method. So the stability condition is then the following. Number 5. If the absolute value of the amplification factor, defined here as the ratio of the Fourier mode at the new time level with respect to the time level, if that is smaller or equal than 1 for the finite difference method, then the finite difference method is stable. That we are going to use now further on. We come back now to what we derived here in a minute, but let me give you one remark. It's a technical remark, but nevertheless it can be interesting when we have solutions that might grow at least for a certain amount of time, or even for the whole time domain that we consider. that might grow, where a numerical solution, where the exact solution might grow. We can also treat that with the finite difference method, but then the condition, the stability condition is slightly different. So that is a more general stability condition. I take that as a remark. So we usually don't use it, but we can use it. So more general stability condition is the following. There should exist some constant c greater 0 such that the amplification factor, and that is then usually the case that it is not only dependent on this combination, on k delta x, but also on delta t and delta x, if that is smaller or equal than 1 plus this constant c times delta t. If that is true for all wave numbers k, for which the k times delta x is smaller or equal than pi, that is all the ones that are really valid, because we have periodicity, then that's all. And if we have times a grid spacing greater 0 and smaller or equal than some limit, and we have the time step delta t greater 0 and smaller some limit, or especially when we get a stability condition, the delta t will be a function of delta x. So this is a little technical. The point is we allow not just a bound 1, but we allow for a growth in delta t. And just to see what this means, then the amplification factor to the power n, that is this g, that will be then this to the power n. So 1 plus c delta t to the power n. And this here, that is, if we think of it, can be regarded as the first two terms of the Taylor expansion of e to the c delta t. So this can then be estimated as by e to the c delta t. This one, and to the power n, we get this. But n delta t is Tn. So that is then e to the Ctn. So then we can get that bounded, and from that we can get the bound then for the solution. Okay. So this is just to allow for an exponential growth when we have that in the solution. But the one that we are going to use is this one. That is. So let us check that stability condition now for our scheme, the forward time-centered space scheme. So we check now our stability condition. That is the one that we are going to use. We just mentioned this condition for your information, but this is the one that we are going to use. We're going to use to check that for the forward time-centered space scheme. And remember, the amplification factor was, I think we had it, I repeat it again, that was the 36, we had it, but I repeat it, g of k delta x is equal to 1 minus 4r sine squared of k delta x half. So that was what we derived. It was the ratio of the Fourier transform at the new time level divided by the old time level. And that is the factor that we multiply each time we apply the scheme. And we look at the Fourier modes. So the condition that we have to check is the absolute value of g of k delta x smaller equal than 1. And there are here two cases that we consider. So, and that is equal to, case 1 is if this is real. And that is in our case. If it's real, then we just have to check that this number, the amplification factor, is between -1 and 1. That is for g of k delta x real. And that is the case what we have. We have a real case, so we can do that. But I also just give you the condition when it is complex. When it's complex, then it's easier to take the absolute value squared. Absolute value squared, that means that we have then the real part of g of k delta x squared plus the imaginary part of g of k delta x squared. And that has to be small equal than 1. So, and that is for g of k delta x complex. So when we have an imaginary part that is not 0. So that is for g of k delta x complex. And this second condition, that is equivalent to the absolute value of g squared. So that is what we consider here. That is the absolute value of g of k delta x squared. So that is then what we are going to check. So we are going to use this function here. Okay, I see we have two visitors. They announce themselves, so we stop here and we take a 10 minutes break, you know, because technology people that they can get back. And please remind me 5 minutes to 10 to stop. Okay, now 10 minutes break, but now the people here, please.
Hey.